Welcome back to the Deep Dive, where we transform your stack of sources,
Yeah.
comprehensive profiles, the dense research, the technical papers, into the most essential and fascinating conversation that gets you truly well-informed.
Our commitment is to synthesize all this information, cut through the sheer volume of facts, and really find those unexpected insights, the aha moments that make the history and the technology truly stick.
And today, we are embarking on a deep dive into a figure who is, well, arguably the true founder of the information age as we know it, Rear Admiral Grace Brewster Hopper.
Her life story is just this magnificent tapestry. It's woven from these threads that seem so disparate. You have advanced mathematics on one hand,
Right.
then this unrelenting military service that spans, 4 decades, and then these completely revolutionary computer science breakthroughs.
When you really look at her career, the sheer scope is it's almost overwhelming. She was a Yale PhD, a Navy admiral, and an architect of global commerce.
But the common thread, the thing that runs through all of those roles, is her relentless fight against complexity. That's the key.
Exactly. We are unpacking a comprehensive biographical profile today, and we're going to trace her journey from a child who literally disassembled her world to figure out how it worked,
I love that story.
all the way through her work on the earliest mechanical computers, and into her final act as the oldest active duty officer in the U.S. Navy.
And our mission here for you is to understand how her technical genius was constantly paired with this really uncompromising dedication to accessibility. We want to grasp the full implications of the concept she championed, machine-independent programming.
That concept, that's the absolute core of her legacy. The idea that programs should be written in English, not mathematical symbols or some cryptic machine code.
It sounds so simple to us now.
Of course. But before Hopper, to instruct a computer, you had to speak its native tongue. And that tongue was assembly language, or worse, just raw binary or octal code. It was a language only a handful of, specialists could ever hope to master.
She fundamentally challenged that assumption, the assumption that computational power was inherently restricted to this tiny, mathematically elite group.
Right.
She recognized that if computers were ever going to move beyond government labs and specialized military projects, they had to be usable by business managers, accountants,
Yeah.
General data processors.
She looked at this incredibly complex, bespoke, just difficult process of programming, and she just declared it inefficient, unnecessarily hard.
Yeah.
And her simple belief that we should communicate with the machine using human language, it required a multi-decade battle against institutional resistance. But it is precisely the reason why you can use a smartphone or run a spreadsheet today. She built that bridge.
It wasn't just a technical invention, you see. It was an economic and really a philosophical mandate. She saw the computer not as some complex calculation engine, but as an indispensable utility for general commerce.
Her work was all about abstraction, building a tool that hid the terrifying complexity of the hardware beneath a simple, clear interface.
That's the perfect way to put it.
Okay, let's unpack this journey. And we have to start at the beginning. Before she was Admiral Hopper, she was Grace Brewster Murray, born in New York City on December 9, 1906.
But the key to her entire personality, her whole career, was this trait she exhibited almost immediately. An insatiable and I'd say disruptive curiosity.
The famous childhood anecdote just illustrates this perfectly. At the age of 7, she was already obsessed with mechanisms. She needed to know what made the clocks tick.
And this wasn't some, passive intellectual interest. This was active deconstruction.
She didn't just look at one clock. The story goes that she systematically dismantled 7 different alarm clocks, trying to figure out the internal mechanisms before her mother finally stepped in.
And confiscated the parts.
Exactly. Limited her future investigations to a single clock at a time.
But that behavior, that drive to just take apart a complex system, understand its guts, and then presumably figure out how to put it back together, that's the blueprint for her entire career in computing. She wasn't satisfied with the black box. She had to see the cogs turning, whether they were actual brass gears or, later, electrical relays.
And what's so fascinating is how that exact same trait shows up decades later after she's retired as a literal philosophical tool.
Yeah.
The sources all mention she had this clock on her wall.
The one that ran counterclockwise.
The one that ran counterclockwise. And that clock wasn't just some quirky decorative choice.
No, it was a prop. It was a teaching tool.
It served as this constant, tangible reminder of her lifelong battle against the inertia of established systems. And the quote that goes with it is crucial to understanding her. She said, "Humans are allergic to change. They love to say, 'We've always done it this way.' I try to fight that.
It just shows she wasn't just a technical innovator, she was a cultural warrior.
Absolutely. If the entire computing world was running clockwise, insisting on complexity, on rigid adherence to assembly code, Hopper was the one running counterclockwise, demonstrating that breaking established patterns was, well, necessary for progress.
And this iconoclasm was forged in a highly, highly rigorous academic environment. Her educational background is so important because it provides the foundation for the precision and the abstraction she later brought to programming.
She attended Vassar College, graduating Phi Beta Kappa in 1928 with a BA in mathematics and physics.
And then moved directly to Yale, which, I mean, that speaks volumes about her intellectual drive at the time.
She earned her Master of Science degree in 1930 and, most significantly, her PhD in mathematics in 1934.
We really have to pause on that PhD achievement. This was the mid-1930s. Earning a PhD in pure mathematics from Yale was an elite achievement for anyone, let alone a woman at that time.
Oh, absolutely.
It placed her firmly in the highest tiers of theoretical academics. Her doctoral advisor was the distinguished Norwegian mathematician Øystein Ore.
And her dissertation title? New Types of Irreducibility Criteria. It just highlights her intellectual depth. This wasn't applied math. This was high-level abstract theory. She was fluent in the language of symbols and extreme complexity.
And this is precisely the connection we need to make for you, the listener. Her deep, deep understanding of theoretical mathematics is what enabled her to see the unnecessary complexity later on.
It's a great point.
Because she was so fluent in symbolic manipulation, she recognized that 99% of the people who needed to use a computer, the data processors, they didn't need that fluency. Her quest for simplicity wasn't born out of an inability to handle complexity. It was born out of a mastery of it.
So she starts teaching math at Vassar in 1931, rises pretty quickly to associate professor by 1941.
Yeah.
So by the time World War II breaks out, she is a tenured, highly respected academic theorist.
A very established life.
A very established life that was about to be completely upended by the needs of the Navy.
And the war, well, it changes everything.
She decides she needs to serve her country. She tries to join the Navy Reserve. But right away, we see a preview of her future battles against bureaucracy. Even just enlisting was a fight.
It was almost laughably difficult. She was initially turned down, 3 times?
3 times.
And the reasons are just this perfect microcosm of the rigid institutional thinking she would later spend her life dismantling. First, she was 34 years old.
Too old.
Considered too old for commissioning. Second, the Navy decided her teaching job at Vassar was too valuable to the war effort for her to leave.
And the third rejection, this one is simply incredible. She was rejected because she was too light.
Right.
The weight-to-height ratio requirement stipulated a minimum weight of 120 pounds, and she was 15 pounds below that.
She literally had to get a weight exemption to serve her country. But Hopper, being Hopper, she persisted.
Of course. She took a leave of absence from Vassar, got the exemption, and was sworn into the U.S. Navy Reserve in 1943, joining the women accepted for volunteer emergency service.
The waves. And again, she excelled. Graduated first in her class from the Naval Reserve Midshipman School in 1944.
She was commissioned as a lieutenant junior grade, and almost immediately she was assigned to a place that would determine the rest of her life. The Bureau of Ships Computation Project at Harvard University.
And this is the moment. This is where the theoretical mathematician meets the physical reality of computing. She was assigned to the programming staff for the Harvard Mark-I computer,
The automatic sequence-controlled calculator.
which was the absolute vanguard of computational technology at the time.
To truly appreciate her role here, we really have to set the stage. What was the Mark-I like? It wasn't silicon, it wasn't electronic, it was electromechanical.
Yeah, that's a term we don't hear much anymore. Imagine a machine that was 51 feet long, 8 feet high, and weighed nearly 5 tons.
This is massive.
It was incredibly loud. You'd hear it constantly clanking as the mechanical relays opened and closed. Calculations were slow. I mean, a simple multiplication could take around 6 seconds. This was a physical giant built of steel and glass, running on electric motors and relays. A beast.
And programming it was a brutally physical process. You weren't typing on a screen. There was no screen. You were literally working with switches and punch cards.
And sometimes manually wiring the machine, right,
Right.
to set up the sequence of calculations.
Exactly. It was a painstaking, labor-intensive process, incredibly prone to errors, and it required immense precision.
And Hopper was one of the very first people in the world to be called a programmer for this kind of machine. Her specific initial task was calculating missile trajectory tables for the Navy.
So, complex partial differential equations that required thousands upon thousands of steps.
All done on this clanking mechanical monster.
And her contribution was immediate. It was fundamental to scaling the practice of computing. She co-authored 3 essential papers on the machine's operation with its director, Howard H. Aiken. But more importantly, she authored what is widely considered the first computer manual.
That manual, a manual of operation for the automatic sequence-controlled calculator, is a landmark document. Think about that for a moment. In an environment that's dominated by trial and error, by sort of, proprietary knowledge.
Yeah, tribal knowledge.
Right. She created the standardized written documentation, the instruction set, that allowed others to replicate and utilize the machine efficiently. She was defining the engineering discipline of computer science before it was even named.
It's interesting to consider the context, though. Here is a Yale PhD mathematician, but in the military structure, she was a subordinate officer under Aiken. Was there ever a tension between her theoretical genius and the practical, hierarchical military environment?
Oh, absolutely. The military environment valued hierarchy and defined procedures, which would naturally clash with the academic mindset of open exploration. But Hopper, she thrived on structure, but only when it led to clarity. Her brilliance, which is shown by her writing that manual, was in translating the operational chaos of a brand new machine into a predictable, logical process that the Navy could actually use. She formalized the process.
So after the war, she wants to transfer to the regular Navy, but bureaucracy strikes again.
She was 2 years over the age cutoff of 38, so she was denied the transfer.
But this administrative roadblock, it led to a really pivotal career choice. She remained at the Harvard Computation Lab as a research fellow under a Navy contract until 1949.
And during this time, Vassar offered her a full professorship, a highly prestigious, safe, established academic position.
And she turned it down.
She declined the security and the prestige of a full professorship to stay with the blinking lights and the whirring mechanisms of early computing.
That decision, it speaks volumes.
It really does.
She recognized that the theoretical world she had mastered was being eclipsed by this new, practical, applied science. She chose the future over the comfortable past. And that choice led her straight into the rapidly emerging and very volatile commercial computing market.
So in 1949, Hopper leaves that academic and military cocoon of Harvard, and she joins the Eckert-Mauchly Computer Corporation as a senior mathematician.
This shift was critical because Eckert-Mauchly was building the UNIVAC, a first large-scale electronic computer designed specifically for the commercial market.
Right, the context here is changing drastically. At Harvard, the goal was scientific calculation. Now the goal was business. It was payroll, inventory, logistics.
Remington Rand later takes over the company, but Hopper stays focused on the UNIVAC, which would hit the market in 1951.
And it was in this commercial setting, dealing with the demands of business users, that she devised the theory that fundamentally changed computing: machine-independent programming languages.
Let's dive into the technical problem she was solving here.
Yeah.
Because it was a huge one.
The problem was one of efficiency and cost. To program the UNIVAC, you still needed assembly language or machine code. This required highly specialized, rare, and very expensive programmers.
And if a programmer made one tiny error, a missing comma, a wrong switch setting, the entire program failed, and debugging was a complete nightmare.
The labor cost and the technical debt were enormous, just astronomical.
And that's where her famous quote about symbol manipulators comes in. She wasn't being dismissive of mathematicians, she was just highlighting the market reality.
Precisely, she stated. Very few people are really symbol manipulators. If they are, they become professional mathematicians, not data processors.
Right.
She saw that the people who needed to run the payroll, the data processors, were fundamentally interested in business logic, not the internal octal code of the machine. They needed clarity and speed.
So she proposed this simple yet profound solution. Create a language based on English, which would then be automatically translated by the computer into the complex machine code required to run the hardware.
This is the moment of abstraction. She introduced the concept of the compiler. It's a brilliant conceptual leap, but it was met with fierce, immediate resistance.
Oh, yeah.
She fought for this idea for 3 years.
And the resistance, it wasn't just technical, it was ideological, it was economic. Why did so many engineers reject the idea so vehemently?
Well, for several reasons. Ideologically, engineers and programmers of the time, they believed they had to be in absolute control of the machine. They thought if you introduced an intermediary layer, a translator, you introduced inefficiency and a loss of control.
And economically.
Economically, assembly language programmers were highly paid, and this new system threatened to democratize their specialized knowledge. It was a threat to their job security, really.
The critics famously told her computers didn't understand English.
And she refuted that by saying, essentially, they don't have to. The compiler understands English, and the compiler then translates that clear human instruction into the language the machine does understand.
She talked about the frustration. She said, I had a writing compiler and nobody would touch it. They told me computers could only do arithmetic.
They were just locked into that mindset, the idea that the input must equal the output in complexity.
But she persisted. In 1952, she published her first paper on the subject, and despite all the internal skepticism, she had an operational program linker, which she named the A compiler, specifically the A0 system.
The A0 system is often mischaracterized as just a translator, but its core innovation was the automation of subroutine handling and linking.
Okay, so what does that mean in practical terms?
Well, before A0, if you needed to calculate a square root, you had to manually write out the complex sequence of instructions every single time you needed it in your program.
Which is incredibly tedious and just begging for an error.
Exactly. A0 allowed programmers to define and reuse blocks of code subroutines by linking them together automatically. You would just call the subroutine by name, and the A0 system would weave the pre-written machine code into the master program.
So it's a birth of modular programming.
It is. It dramatically reduced the amount of raw code a programmer had to write, and it massively increased the reliability of the software. It was a direct attack on the technical debt of manual coding.
And by 1954, Remington Rand, seeing the undeniable reduction in programming time and the subsequent cost savings, they finally embraced the concept.
Right, and Hopper was made the company's first director of automatic programming.
Under her leadership, the department released the next generation of compiler-based languages. Two of the major early ones were mathematic and flowmatic.
And this is a crucial distinction to make.
Mathematic, as the name suggests, was aimed at scientific users. It let them input algebraic notation. But flowmatic, that was the true spiritual predecessor to COBOL.
Absolutely. Flowmatic was designed specifically for data processing, and it used English-like syntax almost exclusively. It was revolutionary.
Programmers could write commands like input inventory file A, move A to B, and compare B with 10.
It was the first time that business people could actually look at a program and reasonably understand what the computer was doing without needing an assembly language dictionary. It was a massive leap forward.
And it's important to give credit where it's due. Hopper's work, it built on the foundation laid by others, showing how innovation really snowballs. The sources mention the Laning and Zierler system as an influence.
Yeah, that was the first compiler to accept algebraic notation as input. It was a parallel development focused on scientific calculation at MIT.
Right.
Hopper's genius was realizing that the same principle of translation and abstraction could be applied not just to math, but to the generalized language of business. And that realization, that set the stage for total industry standardization.
Which brings us to COBOL. Moving beyond internal commercial development, the need for industry-wide standardization became impossible to ignore.
You can see why. If every company has its own unique English-like language, they can't share programs or data across systems. It's chaos.
This led to the formation of the Conference on Data Systems Languages CODISL in the spring of 1959.
This was a landmark industry gathering. You had competitors, government officials, academics, all in the same room. Their goal was monumental. Create a single, unified, machine-independent programming language for business use.
And Hopper was there as a technical consultant, and her influence was absolutely pivotal. They took her proven working model, the flowmatic language, and made it the foundation.
The result, created in record time, was COBOL, Common Business-Oriented Language. It explicitly extended flowmatic, integrating the best ideas from various sources, including IBM's competing language, COM-Tran.
COBOL wasn't just a technical compromise. It was Hopper's philosophical victory writ large. It cemented the idea that clarity was paramount.
It gave the business world the ability to use commands like subtract income tax from pay.
Just contrast that simple, easily audited English command with the cryptic hexadecimal or octal code required to perform the same operation in raw machine language. This change wasn't about elegance. It was about reliability, transferability, and human error reduction.
And the economic impact was massive. Because COBOL was machine independent and standardized, a company could buy hardware from, say, vendor A, write a massive payroll program in COBOL.
And if they later upgraded to a different machine from vendor B, their foundational software still worked.
This concept, portability, was revolutionary. Before COBOL, software was tied to specific hardware, meaning every time you upgraded, you had to rewrite everything.
What a nightmare.
COBOL protected massive business investments and fostered the entire ecosystem of independent business software development. It became the most ubiquitous business language globally, running critical infrastructure right up to the present day.
So her work then transitions from creation to enforcement. After she was recalled to active Navy duty, she served as the director of the Navy Programming Languages Group from 1967 to 1977. She was promoted to captain in 1973.
This is where she embraced the often unpopular role of the standards champion. She was charged with developing validation software for COBOL for the entire Navy.
So she was the quality control.
She was the gatekeeper. She insisted on strict adherence to the standards. If a vendor claimed their compiler ran COBOL, they had to pass Hopper's stringent conformance tests. No exceptions.
Why was this standardization so critical for the military?
Interoperability and cost control. The Defense Department was the largest single purchaser of computer hardware in the world.
Right.
If every vendor had a slightly different dialect of COBOL, moving personnel or data between bases or departments becomes an impossible logistical headache. Hopper's validation tests forced vendors to converge their programming language dialects, saving the Navy billions and ensuring systems could actually communicate with each other.
And this emphasis on standardization leads directly to one of her most incredible forward-thinking insights. One that sounds like she was predicting the modern internet and cloud architecture decades early.
This is where it gets really interesting. The argument for distributed networks.
In the 1970s, the computing status symbol was the centralized mainframe, a massive, expensive computer often housed in an entire room, running everything for a huge organization.
And Hopper looked at this model and she saw profound vulnerability and inefficiency.
She advocated fiercely for the Defense Department to switch to networks of small distributed computers.
It was a deeply controversial stance. She saw the immense processing bottleneck caused by centralization. Instead, she pushed for smaller, cheaper mini-computers distributed across the user base, but all connected.
The key was that users on any node could access common shared databases.
So she was essentially arguing for the power of the network over the power of the single central machine.
Yes, and her rationale was twofold: cost and resiliency. Many computers were far cheaper than mainframes, making computation accessible to smaller departments.
More critically for the Navy, if a large centralized system went down due to attack or malfunction, the entire organization would just halt.
A distributed network provided resiliency. If one node failed, the others could carry on.
She was conceptualizing the architecture that eventually led to client-server models, local area networks, and what we now call cloud distribution. She saw the future of connectivity before the hardware even existed to support it universally.
And this standards work was so effective that the conformance tests she developed for languages like Fortran and COBOL were eventually assumed by the National Bureau of Standards, now NIST. She literally gave the government the tools to reliably procure and manage complex software.
This brings us to the astonishing conclusion of her professional life, the military service that simply refused to end.
She retired for the first time in 1966 as a commander, adhering to the mandatory Navy attrition regulations at age 60.
But the Navy, grappling with the very complexities of standardized computing that she had pioneered, they realized they could not afford to lose her specific institutional and technical knowledge.
So she was immediately recalled to active duty in August 1967.
That initial recall was only supposed to be for 6 months, a quick fix to a standardization problem.
And that 6-month assignment turned into nearly 20 years.
She retired again in 1971, was recalled in 1972. The pattern just continued. Her unique role in ensuring massive federal software systems were compliant and secure made her irreplaceable. She continuously outlasted the normal service tenure regulations.
The promotions followed. She was made captain in 1973. Then, in 1983, President Ronald Reagan promoted her to Commodore.
After a representative on the Armed Services Committee, who had seen her featured on 60 Minutes, recognized her immense value.
The rank of Commodore was renamed Rear Admiral, lower half, in 1985. At a time when female officers were extremely rare, this promotion elevated her to one of the highest ranks in the Navy, cementing her place in military history.
She finally, definitively, retired in 1986. closing out a military career that spanned more than 42 years. At 79 years, 8 months, and 5 days old, she was the oldest active duty commissioned officer in the U.S. Navy.
Her retirement ceremony, it was such a symbolic moment. It was held aboard the USS Constitution, the oldest commissioned ship in the U.S. Navy.
The perfect juxtaposition of the Navy's deep history and its most modern pioneer. She received the Defense Distinguished Service Medal for her dedication.
But the tireless energy, it didn't stop there. Immediately upon retiring from the Navy, she was hired by Digital Equipment Corporation, DEC, as a principal corporate consulting engineer.
At DEC, her role was largely that of a public educator and a goodwill ambassador. She traveled constantly, lecturing to massive audiences, promoting the ethos of ease of use, and sharing the history of early computing.
And this is where we see that rebellious nature shine through again. She frequently wore her Navy full-dress uniform to these civilian lectures.
Despite Department of Defense policy forbidding former officers from wearing the uniform in such circumstances.
She essentially used her senior status to just ignore rules she found pointless. It perfectly captures her blend of dedication and defiance.
She was the rigorous mathematician who became the stern admiral, but always with a playful disdain for unnecessary restrictions. One colleague called her the pirate dying to be released.
And her favorite part of this post-Navy career wasn't the accolades or the salary, but the mentorship. She cited training young people as her most important accomplishment, second only to the compiler itself.
Her philosophy for mentorship was simple, but so powerful. Encourage action and risk-taking. She'd tell them, they come to me, and say, do you think we can do this? I say, try it, and I back them up.
That persistent encouragement to take chances is the spirit of innovation she instilled in an entire generation of programmers.
And she employed some ingenious, really memorable tools to teach fundamental concepts. The most famous, of course, are the nanoseconds. She even brought them onto national TV to demonstrate.
This teaching tool was born out of frustration, right?
Mm-hmm.
People, particularly decision makers, they couldn't grasp the extreme timescales of computation and electronic communication.
Exactly. They would ask her why the satellite link took so long to send a message.
So she needed a tangible analogy.
So she carried pieces of wire, each one precisely 11.8 inches long. This length represents the distance that light, or an electrical signal, travels in a vacuum in 1 nanosecond, 1/1000th of a second.
She called them her nanoseconds.
It's a genius application of physics to engineering. She would use the tiny wire to demonstrate why computers needed to be physically small. If you wanted a calculation to take less than a few nanoseconds, the distance the signal had to travel had to be incredibly short.
If the wires were long, the speed of light, though immense, became the limiting factor.
To contrast, she would then produce this massive coiled length of wire, 984 feet long, representing a single microsecond. This physical contrast instantly explained why minimizing physical distance in hardware was paramount for speed.
Later, she even used tiny grains of pepper to represent picoseconds, trillionths of a second. She made these abstract concepts physically graspable.
The other essential anecdote, of course, is the origin of the term bug in computing. This happened in 1947 while she was working on the Mark II computer.
Right, the Mark II was malfunctioning. Hopper's team traced the issue down and discovered that the source of the problem was a physical, literal insect.
A moth. It had flown into a relay and was physically stopping the electromechanical flow.
They removed the moth and taped it directly into the logbook for that day with the classic deadpan notation. First actual case of bug being found.
Now, while electrical engineers had used the term bug for technical issues for decades before even Thomas Edison used it, Hopper is rightly credited with popularizing the term debugging within the burgeoning computer industry.
And that logbook with the actual moth is now preserved at the Smithsonian Institution.
It's a wonderful reminder that sometimes the most profound technical concepts have the most humble, literal origins.
All these contributions, the compiler, the military standardization, the legendary stories, and the fierce mentorship, earned her the industry's most affectionate title, Grandma COBOL.
Grace Hopper passed away in 1992, but her impact is not historical, it is infrastructural. The sheer volume of awards and namesakes demonstrates how deeply her work is woven into the fabric of our modern world.
She received dozens of honorary degrees, but let's focus on the highest recognition. Posthumously, in 2016, she was awarded the Presidential Medal of Freedom by President Barack Obama, the highest civilian honor in the United States.
During her lifetime, she received the National Medal of Technology in 1991, And the citation, it sums up her entire philosophy beautifully. For her pioneering accomplishments in the development of computer programming languages that simplified computer technology and opened the door to a significantly larger universe of users.
That universe includes every single person who uses a computer today for anything other than pure research.
She was a global figure in this emerging field. In 1973, she was the first American and the first woman of any nationality to be made a Distinguished Fellow of the British Computer Society. And she was inducted into the National Women's Hall of Fame in 1994.
The Navy, which she served for so long, has honored her legacy in some really enduring ways. The Arleigh Burke-class guided missile destroyer, USS Hopper, was named for her.
Affectionately nicknamed Amazing Grace.
Of course. But perhaps the most telling institutional honor is at the U.S. Naval Academy. Hopper Hall houses the Cyber Science Department, and it holds the distinction of being the very first building at any U.S. service academy to be named after a woman.
It just signifies her foundational role in military computation and cybersecurity.
And the modern infrastructure of technology, too, it pays homage. The Cray XE6 Hopper supercomputer, the Google undersea network cable named Grace Hopper, connecting the U.S., U.K., and Spain.
And most recently, the NVIDIA GPU architecture released in 2024 is also named Hopper. She is literally the nameplate on the machines that are powering the modern world.
And her commitment to mentorship continues through the annual Grace Hopper celebration of women in computing.
This conference, inspired by her tireless advocacy and career, has become the world's largest gathering focused on the research and career interests of women in the technical fields. It's the ultimate continuation of her mantra. If the established system tells you no, try it anyway and bring others with you.
So what does this deep dive into Grace Hopper mean for you, the learner? When we analyze the sources, we see a career defined by astonishing technical mastery paired with this uncompromising vision for accessibility.
Her defining legacy is abstraction. She created the compiler concept with the A0 system, she fought for its adoption, and she ensured its standardization through COBOL. She took the arcane and made it clear, expanding the potential user base of computers from a few hundred experts to literally billions of people.
And she did all this while pioneering the fight for modernization in the Navy for over 42 years, constantly running counterclockwise to institutional inertia. Her career is the ultimate proof that challenging the status quo, that we've always done it this way mentality, is the engine of true lasting change.
Her gifts to us are knowledge portability, system clarity, and the courage to simplify.
But here's where it gets really interesting, connecting her historical vision to our modern reality. We spent considerable time discussing how, in the 1970s, Admiral Hopper was fiercely advocating for the Defense Department to switch away from large, centralized mainframe computer systems.
And instead move toward distributed networks. She prized resilience and efficiency through decentralization.
She predicted the systemic risk inherent in putting all computational power in one single basket, advocating for networks where users had local access to common shared databases across multiple nodes.
Right.
Given that foresight, and given that she was the woman who popularized the bug found in a physical computer relay, what would Admiral Hopper, the advocate for decentralized power and user-friendly access, say about the landscape we navigate today? Would she be concerned that the vast majority of our digital lives, our data, our communications, our commerce, is now controlled and funneled through the massive, centralized server farms of just a handful of massive tech giants?
That structure presents the very single point of failure she warned the Navy against decades ago. Only now, that single point of failure is global. So we leave you to consider. Would Grandma COBOL see today's highly centralized digital infrastructure as the triumph of efficiency, or a fundamental architectural bug that threatens the resiliency and freedom of the entire information age?
Think about that. Thank you for joining us for the deep dive.
We hope this comprehensive knowledge serves you well.
Until next time.